All right, let's take a look at the 2015 E&M problem number 2. This is a circuit. You can see that the real battery is split into an ideal part and an internal resistance part. And then we have a variable resistor outside that is connected to a voltmeter. The internal resistance and the variable resistor are in series, so we will just add up those two resistances when considering the overall current. All right, so part A, the measured voltage. So we're going to need to get the overall current here. We're going to use a combination of Kirchhoff's loop rule and Ohm's law. So A part I. We're going to go around the loop and consider the voltage drops around the loop. So we're going to split this real battery into an ideal part and then a resistor. So we're going to have voltage of the battery, and then the internal resistance will bring us down a little bit, and then we will get to the variable resistor that's also called the load, and then we'll be back around. And let's see here, voltmeter reading. Doesn't say anything about the voltmeter not being ideal. Voltmeter. Okay, so we're going to assume that the voltmeter is ideal for the moment. So using Ohm's law, V equals IR. So we're going to have voltage minus IR minus IR equals 0. Now, because the internal resistance and the load resistor are in series, these two currents are also going to be the same. We can factor that out and solve for the overall current is going to be the ideal part of the power supply divided by the total resistance. Now, let's go back at the question and say, what's the measured? Well, the measured voltage is going to be just across the variable resistor. So V sub R is going to be the current times the resistance. Well, this current is this guy, E over little r plus big R. That's the overall current times the resistor. And that's going to be what should be measured by the voltmeter. All right, part 2. What we want is 1 over the voltage as a function of 1 over the resistance. So we're going to have to take this whole thing and flip it upside down. So 1 over the voltage is going to be R plus R over this and 1 over the resistance. Now, technically here I suppose you're done, but that's really not nice. I don't know of anybody who can just look at this equation and say, oh, I know what that's going to be if I graph it. So let's multiply, let's distribute this guy through and see what we get. So 1 over the voltage is going to be little r over ER plus big R over ER. Since we're just multiplying on the denominator here, we have this. Now this is starting to look a little more familiar. These two R's here are the same, so they're going to cancel out. And let's separate this guy out into our variable, which is this big R, and the constants, which are the internal resistance and the ideal part of the battery. So when we're finally done, what we're going to have is something that looks like this. Now, if what we're doing is graphing 1 over V as our Y and our 1 over R as X, what you should see here is the equation of a line, where R over E is the slope and 1 over E is the y-intercept. And these all have a one-to-one correspondence. Get out of my way. One-to-one correspondence, which is why, if you take a look back here, we have a data table where they've given us resistance and voltage, and then they've also given us 1 over and 1 over. That's because they want us to use these specific things to make our graph, which I'm going to have to pause and scroll down so that you can see the graph paper that they have provided for us. All right, we've reset things a little bit, and I've copied the relevant portion of the data table. Now we need to keep in mind that 1 over v is going to be y, and 1 over r is going to be x. So 1 over r goes down here, 1 over v goes up here, and we're going to need units also. So 1 over omega, and this guy will also be 1 over volts. We're also going to need a scale. So we'll put 0 down here in the bottom left-hand corner, and then the r is going to go from 0.1 to 2. So 0.51, 1.52, that sounds good. So 0.51, 1.5, and 2. And what that means is each of the minor tick marks is a 0.1. So each guy in here is 0.1. And then for the vertical scale, I find numbers that are not tiny decimals easier to read and understand. So we're going to go up to, looks like 20 here. So 5, 10, 15, 20. So essentially the same scale, just with a decimal point moved. So we're going to have to say this guy is times 10 to the minus 2 here. And that means all of the individual tick marks along the vertical axis are 1. So as we plot our points, the first one is going to be over to 2 and up to, call it 18. So put a dot there. And then over to 1, and we'll go up to 13.5. So 13.5. 0.5 and 10.6. 0.33 and 9.4. 0.20 and 9.2. And then 0.1 and 8.8. All right, so we have our dots, and they look roughly linear. So we've plotted them, clearly scale line, we did that. Draw a straight line through the data. Well, now I'm going to have to pause again because drawing a straight line is going to take a few tries. Right, here's our line that's reasonably good at fitting, where we have most of the dots pretty close on it, one above, a couple below, and it crosses the vertical axis there, which looks like 5, 6, 7, 8. Looks like it crosses at 8. And then we're going to have to choose another point that looks pretty good. How about that guy? That looks like another pretty good point. Possibly that guy. Okay, so use the straight line to obtain values for E. Well, that's going to be 1 over the y-intercept from our equation up here. And then once we have that, we can use that to find r, which is going to come out of the slope. So our intercept is 8. So 1 over 8. So 1 over 8, 1/8. That looks like a 12.5. Why 12.5 and not 0.125? Well, remember that we messed with the vertical axis by multiplying by, or dividing by 100, so that means we're going to have to multiply by 100. So that'll actually be 100 divided by 8. Gets us our 12.5. All right, then for part 2, I'm going to have slope equals r over e, and our slope is going to be 20 minus 12 over, that looks like 2.3 minus 0.8, 0.8. And again, our vertical axis is times 100th. So these guys are 20 minus 12 divided by 100 divided by 1.5. And then to figure out what R is, we're going to do 12.5 divided by that answer. And it looks like we're getting in the neighborhood of 0.5. No, 0.666. Sorry, I divided when I should have multiplied. So R equals slope times E. And our slope from my graph, yours is going to be a little bit different, is 0.0533. E is 12.5. So that gets a 0.667, and that will be ohms. I'm going to pause again and scroll up again so that I can see parts D and E. All right, part D. Maximum current that the battery can provide is going to be when it is just connected to itself, so the only resistance is the internal resistance. So the maximum current will be E over R, and I got E to be 12.5 volts, and I got R to be 0.667 ohms. So taking those two numbers and dividing them, I got 18.7 amps. All right, part E. We have two voltmeters that we could use, low internal resistance, high internal resistance. So let's take a look at the circuit again. Redraw it here. And our variable resistor is replaced by the voltmeter. And we have E, R, and then another R here. Now, what we want is to lose as little voltage due to the internal resistance as possible. So taking a look back here at this equation, we want I to be as small as possible. In order for I to be as small as possible, we need the total resistance to be as big as possible, because we're going to have the situation where E equals I, then internal resistance plus the resistance of the voltmeter. The bigger the resistance of the voltmeter is, means the lower the current is going to be, and the more irrelevant the internal resistance is going to be. So in order to minimize the current, we need to maximize the resistance of the voltmeter. So what we want is a high resistance voltmeter. So bigger resistance of the voltmeter, smaller current, and therefore less voltage drop due to internal resistance.